Math, 1960, Section 301. You know, summer session number 3. My name is Noon Teng. At this lecture, we're going to discuss about volume of solid of revolution using disk and washer method. So we're going to be using disk in two different scenarios. We use disk method to calculate the volume of solid formed by revolving a region about x-axis. We will use disk method to find the volume of solid formed by revolving a region about y-axis, and we will also use the disk method, the washer method, to find the volume of a solid formed by revolving a region about the x-axis. And then finally we will use the washer method to find the volume of a solid formed by revolving about the y-axis. So first, what is a solid of revolution and what is a disk method? Well, a solid of revolution is like this region here. If we rotate this region around the y-axis, we form this shape. This shape is known as solid of revolution. And then the same thing if we rotate this around the x-axis, we rotate this region around the x-axis, we form this solid of revolution. So what is the disk method then? Well, the disk method is a way of calculating the volume of this solid, a way of calculating the volume of the other solid. So basically, to calculate volume of these two solids, we actually slice up this solid into disks, and we sum up the disks, and the summation or the volume of each and every disk give me the overall volume of each of the whole solid. So solid of revolution. So this is a different solid of revolution here. If we rotate this region around the y-axis, we form this shape which is hollow in the middle. It's different from the other one. The other one is not hollow. This is hollow. It has a donut shape. So and then if we do the same thing, we rotate this region around the x-axis, we form this three-dimensional shape which is also hollow in the middle. The washer method here is a method we use. We slice up these into small washers like this, and we sum up the individual volume of each washer, and when we sum them up, it gives me the overall volume of the whole shape. In details, so the disk method in details. So I do have this region here. I'm going to rotate the region around x-axis. I'm going to form a three-dimensional shape which is known as solid of revolution. And now my task is to find the volume of this solid of revolution. So as we talked about earlier, in order to find the solid of revolution of this shape, we come up with an infinite number of disks. We sum up this infinite number of disks. We sum up the volume of each and every one of them, and we find the overall volume of the solid of revolution. So we're going to derive a formula that we can always use to find the volume of revolution. First, we're going to have a region that is within the following interval A to B. The region we partition it into subinterval n subinterval. So the first subinterval is going to be x0, x1, and then x1, x2, and then x of I minus 1, x of I, x of n minus 1, x of n. So then we're going to have we're going to define delta x. Delta x here being the width of the subinterval. Delta x is going to be b minus a over n. So we're going to define I to be a number from 1 to up to n. So first of all, after we partition the region like this, when we rotate these rectangles, when we rotate them, they're going to form discs. Okay, so the surface area of the disc, which is circular, is going to be a sub I. Okay, you know, I here takes 1, 2 up to n, right? So I take the value from 1 up to n. So the surface area of a circle is equals to pi times pi times uh, f of u sub I squared. So where did I come with u sub I? The u sub I, this is the point at which I'm going to slice each and every disk. I'm gonna slice it at u sub I, where I here takes 1, 2, 3. So u sub I is basically x, you know, could be, you know, x1, x2, xi, and xn. Okay, so then we're going to find the volume v sub I, which is volume of one disk of ice disks. It's going to be equals to pi times f of u sub I squared times delta x. Delta x here is the thickness of the disk. It's the thickness of the disk. Okay, so in order to find the volume, the overall volume is going to be approximately equals to summation of individual disk volume, which is summation from I equals to 1 all the way to n of pi f of u sub I squared delta x. So this is going to be approximation. So if I take the limit as n goes to infinity, I'm going to have the exact volume. The exact volume, we find it by taking the limit as n goes to infinity. In other words, we're going to slice up the shape infinite number of times. delta x. So, and every time we take the limit of a Riemann sum, this sum here is a Riemann sum. When we take the limit of Riemann sum, what do we get? We get integral. So this is the formula we would always be using every time we want to calculate the volume of a solid if we rotate it around the x-axis. Okay, this is a disk method for a volume that we rotate around the x-axis. Okay, here we are going to use the disk method again for a solid that is formed by rotating a region around the y-axis. So we do the same method, but at this time we're going to be rotating the region around the y-axis. Okay, so here you see here this is the disk. So we would have, this is the thickness of the disk, and we're going to find the surface area of this disk. We multiply it by the thickness, and then we sum up the individual disks, and that approximate the whole area of approximate the whole volume, sorry, uh, of the volume of the solid of revolution. Okay, so first we do the very similar thing. So this time we're going to say we have a region which is in between the interval C and D. So this is the interval, right? The region is within the interval C and D. We partition it into y sub 0, y sub 1, y sub 1, y sub 2, and then y sub I minus 1, y sub I, y sub n minus 1, y sub n. So this is how we partition the region that we would rotate. Now we're going to define the thickness of each and every sub-interval. So the thickness would be defined as uh, delta y equals to d minus c over n. I is equals to 1, 2, all the way to n, all the way to n. That's the thickness right there. So what is the surface area equal to? So the surface area, since we have a circular disk, the surface area is going to be a circle, be pi times g sub v sub I squared, and then the volume v sub I, the volume of the disk, is going to be equals to pi times g sub g sub v sub I squared delta y. So to find the overall volume, the overall volume is going to be approximately equals to summation as I goes to as goes from 1 to n pi times e sub v sub I squared delta y. So to find the exact volume, we're going to take the limit as n goes to infinity of summation from I equals 1 up to n of pi e sub v sub I squared delta y. So we take the limit of that, we get when we take the limit of Riemann sum, we get an integral. So this type of integral we're going to be using every time we want to calculate the volume of revolution we revolve region around y-axis. So using the Washer method for to find a solid of revolution about the x-axis. So this is similar. The only difference here is that we're going to have this is something called the outer radius, and then we're going to have the inner radius. So in order to calculate the surface area here, we're going to subtract the inner radius from the outer radius. Okay, just so the volume would be something like that. Okay, so let's see. So here we're going to partition our interval of the region which goes from A to B. We partition it into x of 0, x of 1, x of 1, x of 2, x of I minus 1, x of I, x of n minus 1, x of n. So then we define the thickness or the width of each and every subinterval. So which is delta x. It's going to be equals to b minus a over n. I is equal to 1, 2, all the way to n. So the surface area, which is a circular surface area, equal to pi. This time we're going to have the outer radius f of u sub I squared minus g sub u sub I squared, right? And then to find the volume v sub I, we have the same expression, but we multiply it by the thickness. And in order to find the overall volume, it's going to be approximately equals to summation from I equals to 1 all the way to n sub I. So in order to find the exact volume, we're going to take the limit as n goes to infinity of that expression. So when we take the limit of the Riemann sum, we get integral. So this is the integral we're going to obtain. So using the Washer method to find the volume of a solid revolving about the y-axis, we can always use this formula. We don't need to drive it again because it's similar to the previous derivation. So example 1. Want to find the volume of solid of revolution generated by revolving a region bounded by the graph and graph f of x equal to square root of x and the line x equal to 5. So this is a graph that we can actually sketch. So this is an x-axis. This is a square root function that looks like this. So that's a square root function. If we revolve this square root function, we're going to get a shape like this. So this is the volume. This is the shape that we are interested in finding its volume. So the disk method here, this is a candidate of disk method because it's not hollow. So we say volume using the disk method is equals to pi integral from a to b of f of x squared dx. That means the volume equal to pi integral from 0 to 5 f of x is basically equals to squared dx, so that it's going to be equals to pi integral from 0 to 5 of x dx. That should be equals to pi x squared over 2. We evaluate from 0 to 5, and that should give you 25 pi 2. So use the disk method to find the volume of solid of revolution generated by revolving region, this region here, about y-axis. So first let's try to sketch the region. So the region start here, and that's a cubic function, so it's going to something like this, from 1 to 8. Let's say this is 8 right there. So the region, when we revolve that region, we're going to get a shape that looks like this, from 1 to 8. So we want to find the volume using the disk method. So okay, so volume using the disk method, V equals to pi from C to D of G of y squared dy. So first we're going to express our function in terms of as a function of y. So then we're going to have x equals to y raised to the power 1/3. So then we say V is equal to pi from 1 to 8, right? That's the limit from 1 to 8 of y 1/3 squared dy. So we're going to have pi 1 limit from 1 to 8 of y 2/3 dy. Volume is going to be equals to y raised to the power of 5 3 over 5 3. We evaluate that at 1 and 8, and then we're going to get we're gonna, sorry, here is pi here. We're gonna get 96 over 5 minus 3 5, and that gives you 93 pi 5. That should be the volume. This is cubic squared. It's cubic squared. Okay. To find the volume of a solid of revolution generated by revolving the region bounded by the graph, y is equal to 2 over x and y equal to 3 minus x. So first of all, we want to sketch these. First, I don't know which function is above which function. So I'm going to say 2 for x equals to 3 minus x. Find the point of intersection. That means 2 is equal to 3x minus x squared. That means x squared minus 3x plus 2 is to 0. So here I have x. So x minus 2 and x minus 1. So x is equal to 2 or x is equal to 1. So these are the point of intersection. So if we call the first function, let's call it g of x. So let's say g of x was equal to 2x. That means g of 3 over 2, it's going to be equals to 4 over 3. And then let's call the other function f of x. F of x is equal to 3 minus x. That means f of 3 over 2 is equal to 3 over 2. So that means this point here, 3 over 2, is in the middle of 1 and 2. So it seems like this function here in the interval, this function within the interval, this function is larger than this function. That means when we come to graph the two functions, so the linear function, which goes like this, it's going to be above the other function. So here this is 1, this is 2. So now we're going to find our volume. This is 1 here, this is 2. So the volume here, pi we're going to use a washer method at this point because we have two functions. So integral from one integral from 1 to 2 of, so what is the first function? It's going to be 3 minus x squared minus 2 x squared dx. So then we say pi times the integral from 1 to 2. We're going to FOIL this, so when we FOIL it, we get 9, we get 6x plus get 6x plus x squared minus 4 x squared dx. So then we do regular integration, and then if we calculate this, we should get the answer to this should be equals to pi 3. That's the final answer for this. So find the volume V of the solid of revolution generated by revolving the region enclosed by the graphs y equals to 2x and y equals to x squared about the y-axis. So this is very easy to graph because I have the parabola and the function 2x. So the parabola graph this way usually, right? And then the other one would goes like that. So this is a 2 here. Two functions are equal for a 2. They are equal to 0 at 0. So since I'm revolving around the y-axis, I'm going to express everything in terms of y. So I'm going to have my volume. It's going to be pi integral from 0 to 4, but it should be 0 to, if it was around x-axis, it's going to be 0 to 2, but it's going to be 0 to 4. Okay. At this point, we're going to have the function that we have. It's going to be y raised to the power of 1/2 squared, okay, minus y over 2 squared dy. So then we're going to have pi integral from 0 to 4 of y. So 1/2 times 2, that would be 1, minus y squared over 4 dy. And then we're going to have pi. So when we take the integral of this, we're going to have y squared over 2 minus y cubed over 12 evaluate from 0 to 4, and then we're gonna have pi outside, 8 minus 16 v, and that should be equals to 8 pi v. That's this is cubic units. So that concludes